Welcome. Together, we explore the secrets of the universe. In our new adventure, we head toward our life source, the star that gave birth to our planet, the one that shields us from the darkness and cold of infinite space, and that, one day, will trigger our end. Now take your place, lean back, and enjoy the journey as we travel toward our sun. To fully grasp its importance, let's stretch the laws of physics a little. We go back approximately 5 billion years. The place we arrive in is dark and hazy. There are no planets or stars in sight. What you see is a graveyard devoid of life, a nebula of dust made of various elements. Our solar system does not yet exist. Long ago, another star's life came to an end here. According to theories, this ancient star did not explode violently. It quietly lost its outer layers to space and faded away. But we don't yet know that. What is certain is that everyone you know, everything around you, owes its origin to that very matter. At midday, the sun itself is made of this stardust. Religions may argue endlessly about the origin of humankind, but in truth, the ultimate ancestor of both humanity and everything on our world was nothing but a star that died billions of years ago. In some portions of the nebula, gas and dust begin to clump slowly. You see larger clusters forming. As the mass and volume of accumulation grow, the amount of gas and dust it attracts also increases. This process spans hundreds of thousands, maybe millions of years. At the center of the dust and gas lies something rotating in a great vortex, being heated by friction and pressure. Tons upon tons of matter under enormous pressure and temperature begin to interact so intensely that the vortex's core reaches 14 million degrees, and at that moment, a fusion reaction ignites. Here, the first heartbeat of our beautiful system's king pulses, a torch in the pitch black, the cosmic energy that gives life to its surroundings. A spark ignites. Through the ages, it will guide us like a torch. With the sunrise, by radiating its light, it shines for the first time. A scene around us begins to take shape. Other rotating vortices of dust and gas become the embryonic forms of the prized members of our solar system. First, the gas giants like Jupiter, then the rocky planets, Mercury, Venus, Mars, born from the leftover solid matter, and finally our home, Earth. Isn't it strange? The universe shows us beautifully that every end is a new beginning. The star that died here billions of years ago may once have given rise to a civilization like ours. The destruction that ended its system precipitated the birth of ours. When we consider the vastness of the universe and its 15 billion year age, we see that humankind's significance is almost beyond comprehension. When our sun first formed, it emitted nearly 40% less light than it does today. Over time, on average, that luminosity has increased about 1% every 100 million years. Based on that, scientists believe that Mercury and Venus occupied very different positions back then. Some even propose that Venus may have once harbored liquid water and life. Our vessel moves toward the light. Like a moth helplessly drawn to flame, we approach our sun. This mesmerizing and majestic spectacle still captivates us. For millennia, it has enchanted civilizations and humanity. In many ancient belief systems, you now gaze upon the face of God. Because ancient people attempted to understand nature only by observing, they gazed. They imbued this life-giver, whose presence prevents nature from dying in winter, with sacred meaning. But today, thanks to science and technology, we know you're not looking at God's face, you are looking at a colossal fusion reactor whose core temperature is 15.6 million degrees, where 600 million tons of hydrogen convert to helium each second. The sun's power is far greater than you imagine. In only 3 days, it emits more energy than would be released by burning all natural gas, oil, wood, and coal on Earth. This is more than just energy. If our solar panel technology improved so that 90% of incoming sunlight could convert to electricity, a photovoltaic field of size 25,437 kilometers squared could satisfy the world's entire energy demand. Viewed from afar, the sun that brightens your day and warms your soul is actually an incredibly chaotic, dynamic structure.
Events like magnetic reconnections and plasma bursts occur. Their root cause lies in differential rotation. The sun's deep core rotates around its axis in 7 days, while its outer layers take 24 days. Remember, this body is not solid, but made of plasma. Thus, regional shear flows form. From these tensions emerge potentially dangerous coronal mass ejections. Perhaps in your lifetime you won't even notice, but if by chance a CME is directed toward Earth, you might wake to an electric-charged cave-age morning. Depending on their strength, these charged blasts could incinerate the planet's electronic infrastructure. But what if a truly mega-blast occurs? Recent studies suggest that an event of similar magnitude to ours happened around 10,000 BCE. And so, roughly 30% of climate fluctuations may stem from that era. It is hypothesized that Earth's ice sheets abruptly melted, initiating what's known as the Flood of Noah, driven both by ice melt and atmospheric upheaval, and causing the collapse of ancient civilizations and countless life forms. As Sumerians wrote in detail thousands of years ago, Earth's life, essential and delicate, depends on the sun, yet that sun wields the power to destroy, and someday will. As I said before, the sun is a vast fusion reactor, and like all energy sources, its fuel is not infinite. One day, it will die. When that time begins, our solar system faces massive upheaval. To understand how a star dies, you must know how it works. Stars are enormous masses. Even our medium-sized sun comprises 99.8% of the total mass of the solar system. The planets, asteroids, moons make up only 0.2%. That explains how dense and massive the sun is. Naturally, gravity exerts enormous pressure toward the core, but opposing it is the tremendous outward energy produced from nuclear fusion. For billions of years, these forces balance. Right now, the sun converts hydrogen into helium to produce energy. But hydrogen is not infinite, and the sun is past its halfway point in life. According to estimates, in about 4 billion years, hydrogen in the core will be exhausted, and the sun will begin burning helium. As hydrogen depletes, the outward pressure from fusion weakens, and gravity will begin to compress the core further. The core will shrink, but in doing so, temperature and density rise, eventually allowing helium fusion. Meanwhile, the sun's outer layers will expand, gradually swallowing Mercury and Venus, and maybe reaching Earth's orbit. By then, all water on Earth will have evaporated, and the atmosphere entirely lost. If you were awake to see this birth, you'd see such a scene unfold. This is hardly unlike apocalyptic imagery in holy texts for our planet. The star that once gifted us life now prepares its own end. But even as Earth's demise looms, the sun's expansion may trigger new life elsewhere. Mars, growing hot, might release subterranean water ice. Its atmosphere could rebuild, opening possibilities for life again. The giant icy moons of Jupiter and Saturn, Europa, and Enceladus might thaw, their subsurface oceans emerging and perhaps hosting new life. Never forget, Every end in the cosmos sparks a new beginning. So, has our sun's life journey ended? Of course not. Each day it burns less hydrogen than before. The sun is expected to exhaust helium in about 1.5 billion years. And when that happens, much will change. After helium, the sun would try to fuse carbon, but there's a problem. Carbon fusion requires about 100 million K, and our sun can't reach that. So what happens? Gravity has been compressing the core all along, and when the helium is near depletion, gravity finally seizes its opportunity. The core compresses further once again. But because it cannot ignite carbon strongly enough, the star begins its end stage. This event, occurring in mere minutes, would release more energy than the sun emits over its full 10 billion year lifetime. It's called a thermal runaway. The compressed core reaches the 100 million K threshold and briefly begins carbon fusion. The sun thus inflates, becomes a red giant, and engulfs or incinerates many of its planets. But it only has a small carbon supply, just enough to last a few million years. No matter how gravity compresses it, the core can't reach 500 million K required for heavier fusion. We thus near the end. Our sun, a medium star, will not become a supernova or black hole. Instead, in its long retirement, it will shed its outer layers and leave behind a remnant, a white dwarf no larger than Earth. It's tiny but immensely dense. Just 1 teaspoon of it would weigh tons. Once burning at 100 million degrees, the core now cools, about 100,000 degrees, and over 10 billion years it will slowly fade into a black dwarf. Because the universe is about 15 billion years old, we have not yet observed any black dwarfs. They're predicted to form over 20 to 30 billion years. Now, our sun, having earned its deserved rest, will fade. Our once ordered solar system will dissolve. Outer planets will drift away as gravity weakens. Each member faces a new fate. Until we meet again, stay curious, interpret events as you will, and don't forget to subscribe to the channel. Stay true to reality, real perspective.